Today we are going to discuss CMOS logic. CMOS is complementary metal oxide semiconductor. It's a combination of NMOS and PMOS. Okay, and the CMOS logic has this general structure. The CMOS logic can have two network. One is the pull up network, the another one is pull down network. Between this pull up and pull down network, we have to take the output connection, and pull up network is connected between output and VDD. VDD is plus 5 volts, which is equivalent to logic 1. And pull down network is connected between the ground terminal VSS supply rate, which is equivalent to 0 volts, which is equivalent to logic 0 in digital. And between this VSS and output, we can connect pull down network. This pull up network can be implemented by using PMOS transistors, and a pull down network can be implemented by using NMOS transistor. What is the reason for that? Always the PMOS is a good conductor of logic 1. Conductor of logic 1, and the NMOS is good conductor of logic 0. Okay, so always NMOS transfer logic 0 to the output terminal without any degradation, and PMOS transfer logic 1 from the supply rail VDD to the output terminal without any degradation. That's the reason we have to construct pull up network using PMOS and pull down network using NMOS, right? So what is the meaning of this pull up network? From the name itself we can understand it pulls out the output terminal to VDD. It pulls up the output to VDD, and the pull down network, it pulls down the output to the ground potential. That's the reason. So whenever pull up network is active, that means it is switched on, it transfers the VDD logic to the output terminal, where the output will become 1. And whenever pull down network is active or it is turned on, it transfers the ground potential to the output terminal, so the output will become logic 0. So this is the logic behind this CMOS logic configuration, the general structure. This is actually the static CMOS configuration. Static CMOS configuration. Right? So many CMOS logic configuration have been developed. The very first version is static CMOS configuration. Okay, by using this configuration, how can we implement any logic function? Right? So the logic function can be manipulated by using the Boolean variables, right? So how many input variables are involved? Based on that, how the transistors can be connected to the pull up and the pull down network. So what's the relationship between the input variable and the transistor count? If we have n number of input variable in the logic function, n number of input variable we have in the logic function, we should have 2n number of transistor count. Transistor count become 2n. In this, n number of NMOS transistor we have to use, n number of NMOS transistor we have to use, and n number of PMOS transistor we have to use for implementing the pull up network. This is pull up network for pull up network, and this is for pull down network. So in this way, based on the number of input variable, we can use the transistors in the implementation. Okay, first we can understand how to connect CMOS inverter. How can we implement CMOS inverter and the CMOS buffer circuit using CMOS logic? Okay, CMOS NOT gate and the buffer circuit. Okay, the gate level symbol for CMOS inverter or NOT gate is this symbol. Okay, we have the input variable A and the output Y is equivalent to A bar. Okay, now how this circuit can be implemented. Look at this output function y, which is having only one input variable. So we have to use one NMOS transistor and one PMOS transistor. Okay, this NMOS transistor is connected in the pull down network and this PMOS transistor is connected in the pull up network. Okay, so always try to implement pull down network first, and then the pull up network will be the conduction complement of the pull up network, pull down network. Okay, so what is the symbol for the NMOS transistor, right? So NMOS transistor should have the symbol. It has the gate input terminal and source input terminal and drain input terminal. While drawing the NMOS symbol, try to put the source terminal at the bottom side and the drain terminal at the top side. Okay, so top terminal. In the same way, the PMOS symbol, right, for implementing the pull up network, we have to use PMOS transistor. No, the PMOS transistor symbol is in this way we can draw, right? So the drain terminal should be the top terminal and the bottom terminal must be the bottom terminal must be the drain terminal and the top terminal must be the source terminal, and this is the gate terminal, and here at the gate terminal we have to insert one bubble in the symbol of PMOS transistor. So this is why we can draw the symbol for PMOS and the NMOS. Now how they can be configured in the CMOS logic. Now try to implement the pull down network first between the output terminal and the ground potential VSS. Okay, so here we have to connect one NMOS transistor in the pull down network, right? So this is the gate terminal, this is source terminal and a drain terminal. Always drain must be connected to the output, source must be connected to the VSS supply rate. And in the pull up network, connect this PMOS transistor between output and VDD, right? So use the PMOS symbol in this way and insert a bubble at the gate terminal, and this is the gate terminal, and the drain of the PMOS must be connected to the output, source must be connected to the supply rate VDD, and connect gate terminals of NMOS and PMOS together and connect to input terminal. Okay, this you can consider input A and this you can consider output Y. So this is how we have to construct the CMOS inverter as a CMOS logic in CMOS logic. Okay, so how it functions. So take the truth table for CMOS inverter, right? So take input A and output Y. Okay, and meanwhile we can consider the status of pull down network and pull up network also. Okay, pull down network which is constructed using NMOS, pull up network which is constructed using PMOS. Okay, take the input variable A value as 0, at the time output must be 1. How it happened in the circuit? Look at this. When I am applying A is 0, the gate input of NMOS is 0, gate input of PMOS is 0. So for this input logic, my NMOS will be switched off and PMOS will be switched on. So when the PMOS is switched on, VDD is transferred to the output. So output Y become 1. When A is 0, output Y become 1. So this is how the logic is transferred via this PMOS transistor when the input variable is 0. Right? At the same time, NMOS will be switched off. That means it disconnects the output from the ground potential. Okay. Now, so A is 0, Y output becomes 1. How means? Because my pull up network is switched on, pull down network is switched off. Okay. And when I am going to set my input variable A is 1, my output Y should become 0. How it can be? Pull down network will be switched on, and the pull-up network will be switched off when I apply the A input is 1. We can look at this circuit. When A is 1, the gate input of NMOS become 1, which will be turned on the NMOS transistor. At the same time, the gate input of PMOS will become 1, which will be switched off, which the PMOS transistor will be switched off. So because of that, the output is disconnected from the VDD and it is connected to the ground potential via this NMOS. So output will become 0. Why it will become 0? Because the ground potential is transferred to the output Y. So in this way, the CMOS inverter will be functioning. Okay, so we can understand the functionality of this CMOS inverter. Now, how we can construct the buffer? What is actually buffer? So buffer is the circuit where the output follows the input. So how we can achieve? So in the CMOS inverter, so what is the output logic we can get in variable form? It will be A bar, right? So in general, in CMOS logic circuit, whatever the logic function we are going to implement in the pull down network, that will appear in the output terminal in complement form. So we have implemented A in this pull down network by using single NMOS transistor. This A will appear in the complement form at the output terminal. Okay, so to get the output as an input, output should follow the input means we have to connect one more inverter here. So this information can be given as an input to the another inverter that will complement this circuit function. So we will be getting this is the output. So where the output is equal to A double bar. Here we are applying A bar as an input. So here it will get double inverted. So the double inversion gets cancelled. So output Y will become A. So this is how we can construct the buffer circuit by cascading two CMOS inverter together. Okay. So the another function we can consider, which is called two input NAND gate and two input AND gate, that can be implemented in CMOS logic. Okay, the logic function for two input NAND gate. The gate level symbol is this one. So we can have the symbol, if A and B are the input, output will become A dot B the whole bar. Okay, so this is the two input NAND gate symbol. So we can say the output function Y is equal to A dot B the whole bar. How it is going to be implemented, right? So first of all, take Y. It's a normal form in the targeted variable, which will be A dot B the whole bar. Apply the De Morgan's law, it will become A bar plus B bar. So we can say Y is equal to A bar plus B bar. Now take this function and complement. What will be getting? Y bar is equal to A dot B double bar. Okay. So here the double inversion get cancelled. So how it can be mentioned? So A dot B. So Y bar is equal to A dot B. Why I am writing this one? So when I have the function, I have to check which form of the function should be implemented in pull down network, which form of the function should be implemented in the pull up network. Okay. So this is the normal form of the output variable Y, and this is the complement form of the output variable. Always the complement function has the output logic 0 and the normal or true function has the output logic 1. Okay. So this true function Y is equal to A bar plus B bar, it should be implemented in the pull up network. Okay. and the complement function y bar, which is a dot b, should be implemented in the pull down network. Okay, because the complement function output logic is what? It has the logic value as 0. So always 0 can be transferred via the pull down network using NMOS transistor properly without any degradation to the output terminal. So the pull down network is implemented using NMOS. Okay, and here this y function, which is the normal function, has the logic value as 1. So this 1 can be transferred the output via the pull-up network using PMOS transistor without any degradation. Okay, so this function should be implemented in pull-up and this function should be implemented in pull-down network. Now, what's the relationship between the number of input variable and the transistor count? So here we have the number of input variable. Number of input variable, how many number of input variables we have? 2 number of input variables, right? A and B. Okay, then what is the transistor count? What's the transistor count? The transistor count must be 2 into 2. Okay, I said if n number of input variable we are going to use in the CMOS logic, we should have 2n number of transistors, right? So in this, this is the n value, means your transistor count will become 2n. Okay, so 2 into n. So here 2 number of NMOS we have to use and 2 number of PMOS we have to use. So here totally we are using 2 into 2, 4 number of transistors we are going to use. Among this 4 transistor, 2 transistors must be NMOS transistors and 2 transistors must be PMOS transistor. Okay, so here in the pull down network itself we are going to use multiple transistors, more than 1 transistors. If more than 1 transistors are going to be connected in the pull down network and pull up network, how they can be configured, right? How the transistors, more than 1 transistor, suppose 2 transistors, 2 NMOS transistors we are going to connect in one network, means how they can be combined together, how they can be configured, right? So that's the thing we are going to check. If 2 transistors, first take the pull down network. In the pull down network, 2 NMOS are connected, means AND function can be implemented by connecting 2 transistors in series. Okay, OR function can be implemented by connecting 2 transistors in parallel. This is the configuration we have to understand, right? In the pull down network. The same way in pull up network, if we connect 2 transistors in series, it will implement OR function. And 2 transistors connected in parallel means it will implement AND function. Okay, just pull up network is the conduction complement of pull down network. So to implement AND function, 2 NMOS must be connected in series in pull down and 2 PMOS must be connected in parallel in the must be connected in the yes, for implementing AND function, 2 transistors must be connected in parallel in the PMOS, right? For implementing OR function, 2 transistors must be connected in series in the pull-up network using PMOS transistor. That's the thing we are going to see now. While drawing the CMOS logic, always try to implement pull-down network. Now, take the pull down network, 2 transistors we are going to use, 2 NMOS transistor, right? So connect 2 NMOS transistors in series like this between VSS and the output terminal. Okay, now at the pull up network we have to take 2 PMOS transistors in parallel. Here NMOS connected in series means your pull up transistors PMOS must be connected in parallel, just opposite to pull down network. Okay, take okay. So parallel connection, two drains of both transistors must be connected together. Source of both PMOS transistor must be connected together. Now this is the series connection where one PMOS and one NMOS gate terminal can be connected together, and this PMOS and this NMOS gate can be connected together. Now this can be named as input A and this can be named as input B. So like that, two input variable we can take. For each input variable we have to use one NMOS and one PMOS transistor. Okay, for this input terminal A, this is the A transistor for NMOS, A transistor for PMOS. The same way for input variable B, we have used one NMOS and one PMOS transistor. This is the gate terminal. Assume that this is P1, this is N1. This is P2, PMOS 2 and this is NMOS 2. Okay, so P1, drain 1, source 1 and gate 1. N1, drain 1, source 1 and gate 1. In the same way for N2, how the transistor terminals can be named, right? This can be D2, this is S2 and this is G2. And for P2, PMOS transistor, this is D2, S2, G2. Okay, how they can be configured? D2 and D1 of PMOS must be connected together, right? And S2 and S1 of PMOS must be connected together. That can be connected to supply rail, drain can be connected to the output terminal, right? For the series configuration, just take the N1 first transistor which is directly connected to the output terminal. So that drain must be connected to the output, right? And this S1, that is source terminal of the N1, must be connected to the drain terminal of the N2. So this is called series connection. Here we can consider the node X where the source of NMOS 1 and the drain of NMOS 2 is connected in series. Okay. Then the source of the NMOS 2 must be connected to ground terminal. Now the how the gate terminal connection can be made, right? So the G1 and the G1, that means N1 gate terminal, P1 gate terminal can be connected together. That can be named as the variable A, and the gate 2, that is N2 gate and the P2 gate must be connected together, and that can be where we can apply the B input variable. So this is how two input NAND gate can be implemented. Okay, so we can verify the functionality of this NAND circuit, right, by doing the truth table, constructing the truth table. Take the input variable A, input variable B and the output Y, which is equal to A dot B the whole bar. Okay, so here the pull down network, two transistors connected in series which will generate the product AB. Here is the input A, input B. Here the product AB is generated and which will appear at the output terminal as a AB the whole bar, because we have the pull up network which is the conduction complement of the pull down network. What is the conduction complement? If NMOS transistor are used in the pull down network, PMOS transistor must be used in the pull-up network. Okay, if NMOS transistors are connected in series in the pull-down network, the PMOS must be connected in parallel in the pull-up network. This is the conduction complement. So we can say your pull-down and pull-up network are complement with each other. Okay, now how the circuit is functioning based on the working function table or truth table, we can consider we have two input variable A and B. So we can have the four possible input conditions 0, 0, 0, 1, 1, 0 and then 1, 1, right? So this is the possible value of A and B variable. For how we can interpret the functionality of this NAND gate means, so if any one input is 0 in the input condition, right, the output will be 1. If all the inputs are 1, the output will be 0 for the NAND operation. How it can be achieved with reference to the status of pull up and pull down network. Okay, we can consider the status of pulled up and the pulled down network also. So take, this is my pull down network which is constructed by using PMOS transistors. This is the, pull up network, and this is pull down network which is constructed by using NMOS transistor. Okay, so whenever the pull up network is active, right, so output will become 1. Whenever the pull down network is active, the output will be generated as logic 0. We can check this functionality. Take this input condition 0, 0, right? That means my input variable A is 0 and the output variable B is 0. Okay, so for this condition, for all the gate input, logic will become 0. For all transistor, all whole transistor, the gate input become 0. Okay, so for whenever the gate input is 0, the PMOS transistors will be switched on. So both P2 and P1 will be switched on, and this N1 and N2 NMOS transistor will be switched off. So the entire pull down network will be switched off, which will disconnect the output from the ground potential. So logic 0 cannot appear at the output terminal. But when we consider the pull up network, this P2 receives logic 0 as the gate input, P1 receives logic 0 as the gate input. So both transistors will be switched on, which will transfer VDD to the output terminal. Okay, so for generating the output logic as logic 1, any one PMOS transistor is switched on, automatically the output will become 1 because they are connected in parallel. So that's why for all this logic, the output logic will become 1 because my pull-up network is going to be active in all this combination, right? But the pull-down network will be switched off. Okay, right? So this is how logic 1 is generated at the output terminal. Okay, if we consider this last condition where both A and B are going to be set as 1, right? Try to set and apply the logic. So when we apply this logic, A and B are 1. So G1, G2 of this pull down network, this NMOS transistors will be logic 1, which will turn on the both NMOS transistor, N1 and N2, both will be turned on, right? Because both are connected in series. When both transistors are turned on, which will transfer my VSS to the output logic. So output will become 0 here. Okay, right? So when I consider this pull-up network, since G2 is 1, G1 is 1, right? So both transistors PMOS will be switched off, where the entire pull-up network is switched off, which will disconnect the output from the VDD. So the output cannot become 1. So since pull down network is switched on, which will transfer logic 0 to the output terminal, so my output logic will become 0. So this is how this CMOS NAND gate will function based on this configuration. Okay, if this circuit must be the NAND gate, how the AND gate can be implemented. So look at this output function, which is AB bar, right? If I want to make the function as AB, what should I do? I have to just complement the output function just by connecting my inverter. So if I connect one inverter at this output terminal, the entire circuit will become NAND gate. It will function as a NAND gate. So here I am going to connect one CMOS inverter. This is the output which is generated at the NAND gate as AB, the whole bar, right? So if I connect this inverter, CMOS inverter, at this by using one NMOS and one PMOS transistor, this is CMOS inverter. So where this is the ground logic and this is VDD, right? So now AB bar, AB the whole bar is applied as the input. What I will be getting at the output terminal? AB double bar. The double inversion get cancelled, so I am getting AB output. So here my output Y is equal to AB, which is the function of AND gate. Okay, so this is the AND logic, and here this function is the NAND logic. Okay, right? So what is the NAND gate output is y is equal to AB bar, right? And function is the combination of NAND plus NOT. Okay, so the AND function can be implemented by combining CMOS NAND gate and CMOS inverter or NOT gate. So this is my CMOS NAND gate and this is CMOS NOT gate. These can be combined together to design the AND gate, CMOS AND gate. So this is how we can implement the logic function, NAND logic function and logic function using CMOS logic. Okay. Now, how can we implement 2 input NOR gate and OR gate? The logic function the next logic function, basic logic functions, we can implement 2 input NOR and OR functions. OR function in the CMOS logic. Okay, first take 2 input NOR gate. Okay, the gate level symbol is this one. So if I apply A, B or the input, output is A plus B the whole bar. Okay, so I is equal to A plus B the whole bar. So how can we implement this function in CMOS logic? Similarly, similar to the NAND gate, 2 input NAND gate, here also we are using 2 input variable. So the relationship between the number of input variable and the transistor count, right? So 2 number of input variable we have, we should use 4 number of transistors, right? In this 2 number of NMOS and 2 number of PMOS transistor we have to use. Okay, so how we are going to connect the pull down network and the pull up network? First we have to implement the pull down network. Okay, so for that take this function y is equal to which form of the function should be implemented in pull down, which form of the function should be implemented in pull up, right? If I am taking y is equal to A plus B the whole bar, which can be expanded based on the De Morgan's law, A bar dot B bar. So that means y is equal to A bar dot B bar. Okay, here y normal variable of the output variable we are taking. So this will take the value of logic 1. So which can be implemented using pull up network using PMOS transistor, using 2 PMOS transistors. Okay, the same way if we take the complement of this function y bar equal to A plus B the whole double bar, which is will become double inversion gate cancel here, no, which will become A plus B. That means we have the y bar function which is equal to A plus B. Okay, so this y bar will have the value of logic 0. So always the logic 0, output logic 0 can be implemented using pull down network. Okay, output logic 0 can be generated using pull down network by connecting to NMOS transistor in this configuration, because we have used 2 input variable. Okay, so this A plus B should be implemented in the pull down network to generate logic 0. The A bar dot B bar should be implemented in the pull up network to generate logic 1. So here the dot operator is involved. So we have to use the AND logic. That is, we have to connect 2 PMOS transistor in series. Here the OR logic is involved, right? OR logic is involved in the pulled up network. So we have to connect 2 NMOS transistor in parallel. This is how we are going to implement the NOR function. Okay, right? So in the pull down network, we have to connect 2 NMOS transistor in parallel configuration to implement the NOR logic. take the pull down network, connect to NMOS in parallel. Okay. Now in the pull up network we have to connect two PMOS in series. Okay. At this point you can take the output . Now this terminal we can take A, and this terminal we can take B. This is VDD. Okay, take this is N1, N2, this is P1, P2. Right? So this is source terminal of N1 and N2 should be connected together. Drain terminal of N1, N2 must be connected together in parallel configuration. This is G2, G1 of NMOS transistor. So for this P1, this is G1, this is G2 gate terminal, and this is drain 1, this is source 1, drain 2, source 2. Right? So the source of the P1 and drain of the P2 should be connected together in the series connection. Okay, so this is how we can make the connection between the NMOS and PMOS transistor between the pull down and pull up network. In pull down network, if two transistors are connected in series, the conduction complement of pull up network will become two PMOS transistors connected in, here it is connected in parallel. So in the pull up network, those PMOS transistors must be connected in series. Right? So here, whatever the function we are implementing in the pull down network, that will appear in the complement form in the output terminal. So here two variable A and B transistors connected in parallel, which will implement actually A plus B function. When the transistor switches are connected in parallel, it implement basic OR function, right? This A plus B will appear at the output terminal as A plus B the whole bar because of this conduction complement of the pull down network, which is the pull up network. Okay, so A plus B the whole bar will be the output function. Okay, right? So this is how we can implement two input NOR gate. So if I want to connect the OR function, or I want to implement the OR gate, I have to use one NOT gate at the output terminal of the CMOS NOR gate so that I can get OR function. Okay, take this CMOS inverter by connecting two one NMOS and one PMOS. Right? So this is the output where I am getting A plus B the whole double bar. Double inversion gets cancelled, which will become my y is equal to A plus B, which is the OR function. This is the OR function and this is the NOR function. Okay. So this is how we can implement the two input NOR gate and the OR function. Okay. So up to this portion we can have the NOR gate. If I add one more inverter at the output section, we will be getting the OR function. Okay. So to verify the functionality of this circuit, we have to use the truth table of the NOR gate. If I want to implement the, if I want to verify the NOR functionality, I can take the input variable A and B, verify the output function A plus B, the whole bar. Okay. Take all possible input conditions 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So here how can you interpret this function? If any one input is 1, the output logic will become 0 for the NOR gate. When all inputs are 0, the output logic will become 1 for NOR operation. Okay. How it can be implemented? using this pull down and the pull up network. Just look at this diagram. Okay, so here we have the pull up network, this is pull down network. Apply the logic, right? So here any one logic we can apply, here we can apply 0 0. If you take 0 0, output logic will become 1. Look at this, B is 0, A is 0. If I am going to apply, the gate of all the transistor will become 0, right? So at that time only my pull up network transistor will be switched on. So the entire pull up network is going to be turned on, which will generate the output logic as 1. Okay, so pull down network will be switched off because all NMOS transistor receives the gate input as 0, which will turn off the NMOS transistor. Okay, so here if you apply any one logic, for example, if I am going to take this logic 1 1, so A is 1, B is 1, so all gate input will receive logic 1 as the logic value. Okay, so the NMOS, both N1 and N2, NMOS transistor will be switched on. Here both transistor will be switched off. So the pull-up network is deactivated, right? The pull-up network will be switched off for all this configuration. Okay, pull-up network will be switched off. So especially we are verifying this function of this A value is 1, B value is 1 for this input pattern. So pull-up network will be switched off, but consider the pull-down network, right? N1, N2 receive the logic 1 as the gate input. So both transistor will be switched on. Because of that, what will happen, right? The VSS, ground potential, will be transferred to the output. So the output logic will become 0, right? It is applicable for all this configuration. Okay. Right? So how for these two logic, the pull-up network is deactivated. If any one PMOS is turned on when they are connected in series, right? If any one PMOS is turned off, the logic VDD cannot be transferred to the output. So that's why the entire pull-up network is deactivated, switched off for these three combinations. Okay, this is how the functionality of this two-input CMOS NOR gate can be verified, and if we connect the inverter at the output terminal, we can verify the functionality of OR gate. Our output, how it will become, because our output is the complement of this NOR gate, so this logic will become 0 and this will be 1 1. This is for A plus B function. Okay, so this is how we can construct the basic logic functions. We can implement the basic logic function using CMOS logic. So thank you for watching this video. Thank you.